Welcome back to this NPTEL online certification course in molecular rearrangement and in reactive intermediates. In the last class, I talked about the hydrogen atom transfer, and there I talk about the two important name reaction, the Barton nitride ester reaction, and also I talk about the Hofmann-Laffer-Fertig reaction. And there, if you remember, at the end I was talking about some intramolecular radical cyclization. So I thought about give a separate lecture about the intramolecular radical cyclization, because this is a very important reaction and it was used for several natural product synthesis. Okay, I am going to talk about the Baldwin's rule first, and then I am going to talk about the stereochemistry in the radical cyclization. So what will be the product, so what will be the corresponding diastole selectivity. I am going to talk about some of the oxidative radical cyclization. At the end I am going to talk about one or two reactions using samarium iodide. Okay, so let us start with the Baldwin's rule. So we know about the intramolecular cyclization. So if you go for any type of cyclization to form a ring, then Baldwin's actually proposed a rule. So this is a very important rule. It was used for the if you use a corresponding anion for a cyclization, but here we are going to show that these rules are very similar for if you go for a radical cyclization. And again, there are, if you see, there are some of the, so these numbers is corresponding to the ring size 3, 4 or 5. And here is the tet, trig and dig. These are for the tetrahedral, this is for the sp2 and this is for the sp. So where the the ring cyclization happening on that carbon hybridization we are talking about. So some of them are favored. I think you have already learned this in the Baldwin's rule for the formation of the ring. But what I am going to talk about, the important part in the radical chemistry, what majorly we are going to see is the these two different types. We are not going to see much of this state type of things, but we are going to see mostly the trig and the the diagonal. So we are going to see the trigonal and the diagonal here. Okay, so what we are going to see here, the if you see, you have a radical and you have a olefin, and now how they are getting cyclized. So there could be a exotrig cyclization or there will be endotrig cyclization. Okay, also if you have a alkyne and there is a radical, so then it has a possibility to go for a exocyclization or go for a endocyclization. Again, I think we are going to still follow the very similar rule about the Baldwin's rule, that once the radical is approaching in case of the trigonal one, then it try to approach in such a way so that if this is the sp2 carbon, so it is approaching such a way to, so this angle will be 109 degree. Okay, so that will be the best approach. At the same time, if it is the radical is approaching to the alkyne for the cyclization, then this angle will be close to 120 degrees. So that will be the best approach. Okay. Now we are going to learn that in the endotrig will be in favor or corresponding the exotrig will be favored. Okay. So that I think can be explained from this corresponding tangent state, that the 5 exo versus the corresponding 6 endo, because once you generate a radical species here and you have a olefin, then there is two possibility. It can go for a 5 exotrig to get to this product, or it can go for a 6 endotrig to get to this product. Now again, the relative rate of cyclization is 5 exo is much greater than 6 endo, greater than corresponding 7 endo. Okay. So what is happening? We are saying that this is a kinetically favored product. So this is a kinetically favored product which is forming here. So why it is forming, and you can see here we have also mentioned here the corresponding ring size. When it is 5 and 6 member formation happening here in this scenario, the calculation is 10 to 1 is found is 50 to 1. So you can see there is a preference for the formation of this corresponding 5 exotrig, and this cyclization is, you can see the corresponding the rate of cyclization. Also you can see this rate is much higher compared to this one. So we can explain them from the corresponding the chair like tangent state here. So what is happening? There is a better orbital overlap. Once we are trying to draw this chair like exotangent state, there is a better overlap between this orbital compared to the other tangent state. So that is the main driving force for this for the corresponding exotrig cyclization to happen. See here, I think in this type of reaction you will see that we are going to talk about different type of radical source. X could be a halide, or X could be some other group which can be where the carbon and the X can be cleaved in presence of an initiator, which could be a AIBN tributyl hydride, which can generate this type of radical species which can able to cleave this carbon halogen bond. and to generate a radical, now it can go for an intramolecular cyclization. Okay. Again, you can see that as I mentioned, from this XO trick, can able to make this 5 member, which can go for another hydrogen atom abstraction to get to the corresponding product. Now the question comes, I think initially we have mentioned that when we mentioned that from there it will be going to the XO. Now the question comes, there are different positions. If I give them the numbering from 1, 2, 3, 4, 5. So the problem is, depending on the substitution on this position, there will be a different selectivity, because the question comes, once the radical is attacking here to the olefin, you are generating a methyl group at the end after the hydrogen atom abstraction. So now the question comes, if you are generating these things, the question comes, there will be a 2 methyl group here. Here there is a methyl at the C2 position and there will be methyl at the C5 position. So now are they going to be seen or are they going to be anti? And then which one will be the major one? So that is the answer we are going to find here. So here we can see from this compound, if you try to see, this is going to be the anti, going to be the major, and the seen is going to be the minor. So we try to explain them again, very similar to this chair-like exotangent state. In this chair-like exotangent state, it is the most preferred will be where you can able to put any substitution, you have to find a equatorial position instead of the axial position. You guys know that if you have an axial group in the chair tangent state, then there will be more diaxial interactions. So that is why the tangent will be favored where this group will be in the equatorial position. Now if you see there is a radical cyclization happening, this double bond is actually here in the down. So now this methyl and this methyl will be actually in the opposite phase. The methyl will be, this will be up and this methyl going to form, which is going to be down, okay, going to get to this product. And the other case, what is going to happen, if you try to go for a boat-like tangent state, then only you have a chance of a minor, but this tangent state will have a higher energy. Now we have moved from this C2 to C3 position here. So what is going to happen if I have a methyl group here? What will be the major product? Okay. Again, if you see this type of exotangent state, chair-like exotangent state, again you can see now the methyl will be here, and you have to put the methyl in the, as I mentioned, the methyl will be always in the equatorial position. Once you put methyl in the equatorial position, now this radical has to add here. So now this methyl group will be down, and in this methyl is already down. So this seen product will be the major product. Okay, so this can go for a hydrogen atom abstraction to get to the methyl. And here if you try to go for a boat-like tangent state, that will have a higher energy. So anti will be the minor one. So now we have put the methyl in 2 other position left. As I mentioned the C2 and C3. Now this is the C1 if I give them name, and this will be your C4. So from starting from C1, we are seeing this will be a major product, which is the 2 methyl in the same site. Or if you start from this C4 methyl, then the major where these 2 methyl will be in the anti position. So what is happening here? You can see we are making the very same product, but in one case they are seen, another case they are anti. So now if you try to explain them very similarly what we have tried to explain in the previous case from this chair-like tangent state here, again the idea is you always try to put this group in the equatorial position. So this is for this one. What is going to happen here? We are showing here this will be in the equatorial position. Now once this radical is attacking here, this both of the methyl will be actually in the same side. They both will be down, okay, to forming this compound. And then again what is going to happen once you are here in this scenario, we can draw this corresponding tangent state here. What is going to happen now here, in methyl is in this position here, okay. Sorry, I think it will be the wrong position we have drawn. So actually we are talking about the methyl in this position, because that is a position where the methyl will be. And as I mentioned, so there will be a hydrogen here, we can say this is H. In this position there will be methyl up and there will be a hydrogen here in there. So the axial position will be this hydrogen, equatorial position will be the methyl. Now once this radical cyclization is happening, this methyl will be down, this methyl will be up. So you end up getting to the corresponding anti product as the major product. So now as I was mentioning, in all the different cases you have seen this corresponding 5XO trick is the major product. What is happening in this reaction, we are end up making the 5 member ring. So it is very useful to make this type of periodic ring. Now depending on the group you have, if you have a bromine versus iodine versus chlorine, you can see their bond dissociation energy. So depending on the bond dissociation energy, the one will be faster versus the other. And also what is actually often is getting observed in this intramolecular radical cyclization, the smaller size ring is forming faster compared to the larger size ring. Okay. Again this could be for the entropy factor. Here I am going to show you another example here. If you have a tributyl tin hydride and the corresponding AIBN, again you know that it is going to make the corresponding tin radical, which will cleave this, generate the radical species here. This radical can participate in the so you can see so this will be a nucleophilic radical. I am sure you have learned about the nucleophilic radical. So which is going to act to a alpha beta unsaturated compound. So that will be a olefin with the electron withdrawing group, and you have a nucleophilic radical here, okay, which is adding. So now if you see again, I think is forming a 5-member ring here, okay, and you can see so this is the product going to be the major product where these two group will be. You can see here so this is already off, and so this you can draw here, this is already off. Now you can see once this bond is forming here, this will be down to avoid the steric class in the corresponding tangent state, to giving this product as the major product. Another example here. So if you see about this, I think so this came in the exam. So if you, I think the one of the important factor that if you think about the corresponding cyclohexane geometry, these two groups are not same side, they are anti. So what is happening in the reaction? We are end up getting to a radical here, which is going to add to this corresponding. You can see this is a nucleophilic radical which is going to add to this corresponding alpha beta unsaturated carbonyl compound, and going for a 5-exo trick, and then it will go for the hydride abstraction for tributyl tin hydride to get to this product. Another interesting example, this is also came in the exam, that if you start with this compound using tributyl tin hydride and AIBN, what will be your product? So you can see this will be your product at the end. So let's try to understand how this is thing happening. So you can see that once you have this AIBN tributyl tin hydride, I have already mentioned you are generating tributyl tin radical, which is going to cleave this carbon bromine bond. After the debromination, it will generate a radical species here. We can draw the radical like that. And now if you try to draw this corresponding conformation, now you can understand that after formation of this radical, you have so this is a vinyl radical which will be very reactive. At the same time, it is going to add to this corresponding alpha beta unsaturated carbonyl compound here. So there will be radical addition here, formation of this species, and then in this case what is going to happen from there, it is going to go for a hydrogen atom abstraction. So it will go for hydrogen atom abstraction from this tributyl tin hydride to get to this corresponding product. Another important example here, in this particular compound you just have to look for if it, so actually this also came in the exam. So what is going to happen if you take this compound tributyl tin hydride under H nu, again the tributyl tin radical which is going to form here, going to generate this corresponding radical is a vinyl radical, as I was mentioning in the last slide. What is happening here, from this vinyl radical to come and add to this alpha beta unsaturated carbon will be very difficult, okay. So instead of that, what is going to happen, it is going to go for a hydrogen atom abstraction here, 1,5 hydrogen atom abstraction, because the other cyclization will be, you can see if you want to cyclize, then it will be 1, 2, 3, 4, 5, 6, and as I was saying, there is a we talk about 5-exo, but this is going to be 6-exo here. So that's why it will go for this 1,5 hydrogen atom abstraction, because these are very reactive radicals. And if you mention, I have already mentioned that if you have vinyl radical, then the hydrogen abstraction rate will be much faster compared to the corresponding alkyl radical, okay. And then it will going to form this corresponding vinyl corresponding allyl radical which will be stabilized, okay. So once you have this allyl radical, now what is going to happen, it can now go for a radical addition here to this double bond, okay. So it will be a 5-exo trick cyclization again going to happen to form this corresponding product. Another important example again which came in the GATE exam. So what is going to happen from here? If you use tributyl tin hydride AIBN, what is going to happen? First there will be cleavage of this carbon bromine bond in a homolytic cleavage to generate a radical which is going to you can see here in this place there is no other things except there is a double bond here. It will definitely go for adding to the double bond to generate a radical species here. Now you have a strain rings. So once you see you have this type of a cyclopropane where you can see there is a double bond attached with the corresponding cyclopropane, then they are, once you add a radical, they are prone to radical, so they are prone for the cleavage, so that can cleave here to generate radicals. Okay. So that is very similar thing happening here. This is going to open this corresponding cyclopropane, and you are generating a stable radical. It is a radical next to the ester, and then what is going to happen, it is going to take a hydrogen from the tributyl tin hydride to get to the corresponding product. Another interesting example here, this also came in an exam. So what is happening here, you can see there is a carbon bromine bond going to get cleaved to generate a radical, which is going to add here to the double bond first, and then it is going to add to the triple bond. So you can see here what is happening here, it is first a 5-exo trig happening, okay, then there is a 5-exo dig happening here to get to this this compound. So you can show here in the mechanism, okay, so which will finally go for a hydrogen atom transfer to get to this product. So now we are talking about, so we already talk about the radical cyclization in case of when you have olefin. Now we are talking about when you have alkyne here, and here your first thing is tributyl tin hydride and AIBN. You are generating this product where you can see this group is actually and opposite side of this methyl. So you are getting this product with 98 to 2. So E versus Z selectivity. Here E versus Z selectivity, your Z is major. You are getting the product where this ester and the methyl the same side. That means the E to Z is 11 to almost 90-10. So but here the difference what you are making here, you are using a different hydrogen donor. So you are using this TMS3 SiH versus a tributyl tin hydride. So the important thing is, first thing, once this radical is going to form, so here it is forming from the AIBN, here the corresponding boron and oxygen, the trialkyl boron. I am going to explain them again in more details when I am going to talk about the organoboron chemistry. Then once you treat this trialkyl boron with the oxygen, it will generate a alkyl radical, which is going to cleave this carbon iodine bond here to generate this radical species. Now it can go for, once you form the radical, it will go for this intramolecular radical cyclization. It will come to this type of intermediate species, but here the important catch is that it can able to go for from this step to this step. So there could be internal isomerization is happening, because once you see that these one cases, you can think about the ester on this side compared to the other side. But depending on, now the question is what type of the hydrogen acceptor you are using. If you are using a less bulkier corresponding tin hydride, the tributyl tin hydride, then what is happening, the radical abstraction happening from the thermodynamically favored isomer, because this will be thermodynamically favored compared to this, because you can see here the methyl and this group are have a steric class compared to this one. So this will be thermodynamically favored isomer. So if you have a the less bulkier size the hydrogen donor, then it will going to form this product after the hydrogen atom abstraction. But if you have a bulkier one here, then what is going to happen, it is going to go from this particular intermediate, because what is going to happen, it cannot go from the other one because this type of the hydrogen donor going to have a steric class also. Okay, that's why it is going to abstract from. So it is going for the hydrogen abstraction from here in case of this particular silane, and going to get to this product as a major product. Another important example here, tributyl tin hydride and the AIBN going to generate the radical here, which is going to go for the intramolecular cyclization. Here you can see it is going to attack here, and then it is going to form this compound after the, so it is going to attack for a radical attack going to happen. You can see this is a happen to this double bond. If it is going to other double bond, then the ring size will be bigger. So it is going to attack here to form this compound, and then once you use the the Jones reagent, it can going to convert this one to corresponding lactone. There is another example here where it is generating this type of nitrite radical from this compound under the H nu. The nitrite radical is going to attack to the alkyne, and then it is going to form this species here, which is going for 1,5 hydrogen atom transport, because this is a vinyl radical which will go for a hydrogen atom abstraction. As I mentioned, the vinyl radicals are much more reactive, and their reactivity for the hydrogen atom abstraction is much faster. So then it will generate this type of stable radical species which can now go for this addition reaction, because you have this corresponding double bond here, which can go for a 5-exo trick and going to form this product. At the it is going to get to this NO2 going to get out, and then it is going to generate a radical here. So there will be O dot, and then there will be carbon dot, which can finally convert to corresponding carbonyl. So now I am going to talk about some of this chemistry I have already mentioned in the samarium chemistry when I was talking, but here I am going to again explain you that I think I have already mentioned that once you use samarium iodide, what is going to happen? It is going to reduce this corresponding carbonyl compound. Here you have the carbonyl and the ester, but once you have this 1,3-diketo, it is going to make a chelate. Okay, it is going to form a chelate here, and then it is going to, first thing, it is going to form this type of the samarium ketyl radical. So I think there is a error here. I think this will be H instead of the OAT. So sorry for that. So instead of the OAT, this will be H. So samarium going to make a radical here, ketyl radical, which is going to go for addition to this carbonyl group. Now what is happening? Samarium actually binding with these two oxygen. So one of the important thing is, once this is binding, these two oxygen and the newly formed the carbon oxygen bond after the radical addition will be in the same site. Okay, so both of these oxygen will be same site. So you can see in the product you make a 1,2 diol where these two OH will be in the same site. And another important thing is here there is a dipole things here. So there is a minimization of the dipole happening here in this tangent state. In this particular tangent state there is a minimization of dipole, which allowing this corresponding exo trig cyclization, which I mentioned, and then after them the samarium is getting out in place of the H plus to get to this corresponding product. Here another example of this particular reaction. Here what is happening, very similarly as you seen, samarium is first forming the corresponding samarium ketyl radical after the reduction of this carbonyl group here, and then once it is generated in this ketyl radical, it is going for this exo trig cyclization as I mentioned. And after the exotic cyclization, here you can see from this, again I think I have already mentioned the samarium chemistry. The samarium can add with this radical, then there will be acetic anhydride going to come replacing samarium, and at the end what is going to happen, you end up forming this corresponding product. Okay, again you can see we try to explain this the formation of this corresponding product from this tangent state, where you can see in this exo trig tangent state where you have this oxygen here. Okay, you can see there that in this difference, so there is a steric strain going to happen versus this. Okay, there is a tandem radical cyclization here in this compound. Again you can see there is two double bond here. Once you form this radical, it is going to go for this first radical cyclization here. It is going to add here, you can see this is a nucleophilic radical, it will going to add to this alpha beta unsaturated radical, that will be the more preferred one. First the 5-exo trig going to happen, and then the next thing is there will be another 5-exo trig going to get up, because this is a radical which is going to form here next to a carbonyl group. So this is becoming a electrophilic radical. So now this electrophilic radical will going to prefer to add to a corresponding double bond, and once that is happening, you can see what we have mentioned at the beginning. If you remember this 5-exo trig cyclizations, you have end up making the syn product at the beginning when I was talking about at the first slide when I was talking about this corresponding chair like exotangent state. So first it will be once the first cyclization happening, they are in the syn geometry, and again the next cyclization happening the 5-exo trig given this particular product after the hydrogen atom abstraction. So in this particular part, what I have talked about, I have talked about the intramolecular radical cyclization. I talk about why the 5-exo trig is favor compared to the 6-endo trig. I have also talked about the several different variation of this reaction. If you bring different substitution in the different position, that then the selectivity varies. Okay, and then at the end I talk about some of the samarium catalyst intramolecular cyclization, radical cyclization reaction. References, and thank you for the coming to the class, and I am going to see you guys in the next class. Thank you.